We will begin this module by explaining the basic concept of the fly-by-wire system. In conventional aircraft, the movement of the control column is transferred along cables and pulleys until it reaches the control surface to be moved. In the A330, A340 family, however, the cables and pulleys have been replaced by electrical wires. This has the advantage of saving weight on the aircraft. However, there are even greater advantages, as the video clip will demonstrate.
Now the way became clear to reassess the mechanical linkages, transferring the control commands to the electrically actuated hydraulic motors that work the flying surfaces. As electrical signals were already being used to control the motors, the logical step now was to send the message to them direct from the control column by electrical wire, resulting in a far simpler and lighter system. And without the need to exert muscle power, the conventional control yokes could be replaced by small side sticks.
The electrical signals created by side stick movement travel through flight control computers before being passed to the flight control surface hydraulic actuators, also named servo controls. These computers analyze the signal to check that it is a safe command and ensure the optimum flight control surface deflection for the demand. This has advantages over conventional systems. It makes the aircraft extremely stable, enhances safety, reduces the workload of the pilot. Let's now look at the flight control surfaces themselves. The flight control system incorporates ailerons, elevators, a trimmable horizontal stabilizer, THS for pitch trim, a rudder, ground spoilers, speed brakes. Now let's introduce the ECAM flight control page. You can see that all the flight control surfaces we have talked about are displayed. We will now see them in more detail. The movements of both ailerons and both elevators are symbolized by a green index moving in front of a white scale. The green rudder symbol is used as an index to display the movements of the rudder on a white scale. The rudder trim is indicated by a small blue line below the scale. Note that the rudder and the pedal deflections are limited as a function of speed via a rudder travel limiter. The high speed position is indicated by small green lines on the rudder scale. The pitch trim position is indicated by THS deflection in degrees up or down. Let's continue with the spoilers. The spoilers have several functions. Speed brakes use all the spoilers. Roll control uses the 5 outer spoilers. On the video, look at the left spoilers as they deploy, then at the right ones as the wings are leveled. Click on the video window to start it. Ground spoilers use all surfaces. On the video, watch as all the spoilers
Click on the
deploy
video
at
window
touchdown.
to start it.
On the ECAM flight control page, the spoiler extended position is indicated by small arrows. This is the speed brake case. All these control surface indications will be explained in more detail in the normal and abnormal operation modules. Now we will look at the flight control computers. The movements of the flight control surfaces are managed by 5 computers. These are 3 primary computers, prim, 2 secondary computers, sec. In addition, 2 flight control data concentrator computers, FCDC, are used to acquire data from the prim and sec. Then, they send it to the EIS. The status of prim and sec is indicated on the ECAM flight control page. The other computers are not displayed. These indications will be seen in more detail in the abnormal operation module. Now we will see the hydraulic aspect. 3 independent hydraulic systems are used to power all the flight control surfaces. The hydraulic systems which actuate each control surface are indicated on the ECAM flight control page by the use of G, B, and Y. For example, the rudder is powered by the green, blue, and yellow hydraulic systems. The ECAM flight control page is now complete. Pilots control pitch and roll through 2 side sticks. There are associated side stick priority lights. Side sticks and priority lights will be explained in a separate module. Pitch trim wheels are located on the center pedestal. There are 2 sets of conventional rudder pedals. A rudder trim panel is located on the pedestal. A speed brake lever is located on the left side of the pedestal. In addition, there are 2 panels located on the overhead panel to control the flight control computers. Now we will introduce the lift augmentation devices. There are 7 slats on each leading edge and 2 flaps on each trailing edge. The slats and flaps are hydraulically actuated like all the other surfaces. They are electrically controlled via 2 slat flap control computers, SFCC. Each SFCC has 2 channels, one for the flaps and one for the slats. Each channel can drive its associated surfaces. The flap lever, located on the right side of the pedestal, operates the slats and flaps. The flap lever has the following positions: 0, 1, 2, 3, and full. The flaps and slats information is shown on the engine warning display. The flap and slat positions are indicated by white dots. Here, the surfaces are extended to position 1 plus F. This is flap 0 indication. Notice there is no labeling with this setting. The slats and flaps are fitted with protection functions. In particular, surface asymmetry between left and right wing, surface attachment failure, overspeed or uncommanded movement are detected. All these protections will be seen in detail in the abnormal operation modules. In the A330-A340 family, manual roll and pitch are controlled by the side sticks. They are spring-loaded to neutral and receive no feedback from the flight controls. Movement of one side stick will not cause movement of the other. In this case, as the left side stick is moved, the right side stick remains in the neutral position. All side stick commands are processed through the flight control computers before being sent to the control surfaces. You can see that as one side stick is pushed forward, the elevators move down in response. If both side sticks are operated at the same time, their deflections are algebraically added together. In this example, as the side sticks are moved in opposite directions, the elevators remain in the neutral position. When both side sticks are moved in the same way, the total demand is never more than full deflection on only one side stick. Here, as both side sticks are moved forward, the elevators achieve normal full-down deflection, but not more. When either autopilot is engaged, both side sticks lock into their neutral position. Notice that if a pilot applies sufficient force, the side stick becomes free and the autopilot disengages with audio and visual warnings. Move the left side stick. The autopilot has disengaged. The associated audio and visual warnings will continue until canceled by the crew. As you will perform this many times in your simulator sessions, we will now continue with the autopilot disconnect and takeover push button. The autopilot has been re-engaged for you. Each side stick is fitted with a red autopilot disconnect and side stick takeover push button. By pressing it, a pilot disconnects the autopilot. Disconnect the autopilot. Notice on the FCU that the autopilot has disconnected. In this case, the associated audio and visual warnings can be canceled by pressing the autopilot disconnect push button a second time or will stop automatically. A side stick priority logic is also available. Let's study it in more detail. By pressing and holding the takeover push button, a pilot can deactivate the opposite side stick. Audio and visual indications are provided to identify which pilot has control of the aircraft. You are sitting on the left. Take priority.
Priority left.
You heard the audio warning. Notice there is also a red side stick priority arrow in front of the first officer, indicating that his side stick is inoperative. The arrow points left, showing that the captain has control. If the first officer had taken over, the message would have been priority right, and the red arrow in front of the captain would have been illuminated. To see what happens when the deactivated side stick is moved, move the first officer's side stick. A green light illuminates in front of the pilot who has control of the aircraft. Here, Captain. As soon as the deactivated side stick is returned to neutral, the green light extinguishes. If both pilots press their takeover push button, the last one gets the priority. If it is necessary to deactivate the opposite side stick permanently, press and hold the takeover push button for at least 40 seconds. To reactivate a permanently deactivated side stick, either pilot has to press his takeover push button momentarily. Notice that both side stick priority lights are extinguished.
Dual input. You heard the audio warning and saw both green side stick priority lights flash, indicating a simultaneous control input. Simultaneous control inputs are never recommended. If the pilot non-flying must make a control input, he must press his takeover push button. We will now study the normal law module.
In this module, we will be looking at how an A330 pilot and the aircraft computers interface to ensure safe and accurate flight, with minimum workload for the crew. In this module, we will be looking at how an A330 pilot and the aircraft computers interface to ensure safe and accurate flight, with minimum workload for the crew. For clarity, most references in this module will be made to manual flight inputs. However, the references apply equally to automatic flight, unless stated otherwise. A side stick or an autopilot sends a message to the flight control computers, demanding an aircraft maneuver. The flight control computers process the demand and send it to the control surfaces. The processing uses preset limitations and instructions called laws. The aircraft responds conventionally to the movement of control surfaces. Normal law is modified depending on the flight phase. It operates in 3 modes. Ground mode operates on the ground when the aircraft is electrically and hydraulically powered. Controls are conventional. Flight mode operates in the air after a gradual transition from ground mode just after liftoff. Will be discussed in detail later in this module. Flare mode modifies flight mode to introduce a conventional feel to the landing phase. Will be discussed later in this module. We will compare a conventional aircraft, an A310, with the fly-by-wire A330 in normal law flight mode. Control surface deflection is directed proportional to control yoke deflection. The same yoke input produces a higher rate of pitch roll at high speed, lower rate of pitch roll at low speed. Control surface deflection is not directly proportional to side stick deflection. A side stick deflection gives a rate demand to the flight control computers. The flight control computers set control surface deflection to meet the rate demand. For the same side stick input, the control surface deflections will be large at low speed but small at high speed. A side stick input is a rate of roll demand in roll, load factor G demand in pitch. Yaw control is conventional. Remember, the A330 responds conventionally to the movement of control surfaces. However, unconventionally, the response information is fed back to the flight control computers. The computers process this feedback and adjust control surface deflection to ensure that the maneuver rate demand is executed accurately. This means that control surface deflections may be altered with no change in side stick position. In flight mode, if, for example, you wish to execute a descending left turn, you set the required attitude and then return the side stick to neutral. The neutral side stick position demands 0 rate of pitch and roll. The flight control computers will maintain the set attitude until you use the side stick to demand an attitude change. Throughout the maneuver, there are no pilot trim inputs. Turn coordination and Dutch roll damping are automatically provided in normal law. Pilot inputs on the rudder pedals are not required. Normal law provides a number of airborne pitch protections. They are maneuver protection, pitch attitude protection, high angle of attack protection, high speed protection. In lateral control, there is only one protection, which is for bank angle. Let's take a closer look at these protections. In a conventional aircraft, pilots must ensure that structural limitations are not exceeded. However, in the A330 family, maneuver protection is available in normal law. Maneuver protection prevents structural overstress by limiting control surface deflections through the flight control computers. Full side stick movement is always available. The structural limitations vary with configuration. In clean configuration, between positive 2.5 G to negative 1 G, flaps extended between positive 2 G to 0 G. As with the maneuver protection, if the aircraft reaches the pitch attitude protection nose-up limits, then the flight control computers will override pilot demands and keep the aircraft within the safe flight limits. The pitch attitude protection limits are shown as small green dashes on the PFD. Note that the pitch-up limits vary between 30 and 25 degrees, depending on the aircraft configuration and speed. In the nose-down case, the computers will limit the nose-down attitude at 15 degrees. The high angle of attack protection is designed to prevent the aircraft from stalling and to ensure optimum performance in extreme maneuvers, such as wind shear or GPWS warning recovery. This protection takes priority over all others. This protection displays information against the PFD speed scale. As speed decreases, it reaches VLS, lowest achievable speed with autothrust engaged. With autothrust inoperative or not engaged, the speed can reduce to the first level of angle of attack protection, V alpha prot, which is shown at the top of the amber-black band, barber pole. The flight control computers will maintain the speed at V alpha prot. If engaged, the autopilot will disconnect. If the pilots override V alpha prot using the side stick, the speed can reduce to V alpha max. In normal law, the flight control computers will maintain V alpha max, even if a pilot holds a side stick fully aft. Nose-up pitch trim is inhibited. In the protection range, the normal law demand is modified, and side stick input is an angle of attack demand instead of a load factor demand. Provided the autothrust is serviceable, the speed is unlikely to reduce to V alpha max before the alpha floor protection is triggered. This is indicated by an alpha floor indication on the FMA and also on the engine warning display. If the pilot releases the side stick at V alpha max, the speed will return to and maintain V alpha prot. The protection we will look at now is the high speed protection. It is designed to prevent the aircraft from exceeding maximum speed. These protection limits are displayed on the PFD speed scale. VMO-MMO is shown at the bottom of the red-black barber pole. Green dashes indicate the speed at which the protection is activated. When the airspeed Mach increases above the VMO-MMO, an overspeed ECAM warning is triggered, as shown on the autoflight chapter. If the airspeed Mach increases to the protection speed, the autopilot will disengage and the flight control computers send a pitch up command to the control surfaces to prevent further acceleration. The flight control computers will permit this speed to be momentarily exceeded for maneuvering if necessary, but will then return to the protection speed. Notice that the pilot cannot override the automatic nose pitch-up. Under normal law, bank angle protection limits the angle of bank to 67 degrees, shown by green dashes on the PFD. If the pilot holds full lateral side stick, angle of bank will increase and maintain 67 degrees. The flight director, FD, on the PFD will disappear if the angle of bank exceeds 45 degrees. If the side stick is released at any time when the bank angle exceeds 33 degrees, the aircraft will return to and maintain 33 degrees bank angle. The FD will be displayed again on the PFD when the angle of bank reduces to less than 40 degrees. Auto trim is inhibited above 33 degrees. Note, if high speed or angle of attack protections are active, angle of bank is limited to 45 degrees, and the aircraft will return to wings level if the side stick is released. We will now study the reconfiguration laws in the next module. A single failure cannot result in the loss of normal law. However, multiple failures of flight control, hydraulic, or electrical systems may result in a degradation of the flight control law. The level of degradation will depend on the severity of the failures. Degradation of the flight control laws is sometimes referred to as reconfiguration. We will study these degraded laws in order of increasing severity. In alternate law, ground and flare mode are as in normal law. Flight mode, pitch control, load factor demand as in normal law. Roll control, conventional. Surface deflection is proportional to side stick deflection. Roll sensitivity is proportional to airspeed. Feels more sensitive. Yaw control. Damping available with limited authority. Degradation to alternate law is indicated by the ECAM caution. Flight control, alternate law. Protection lost. You will see this caution in detail in the abnormal operation module. Under alternate law, most protections are lost. Some are replaced by stabilities. We will continue by studying the loss of protections. Pitch attitude protection is lost, and the flight control computers will not limit the nose up or nose down pitch attitude. On the PFD, the green dashes which mark the protection limits in normal law are replaced by amber crosses. Bank angle protection is lost. On the PFD, the green dashes are replaced by amber crosses. The maneuver protection is similar to normal law, so we will go straight to the differences between normal and alternate high angle of attack protection. In alternate law, the high angle of attack protection is replaced by a low speed stability. V alpha prot and V alpha max are replaced by a stall warning speed, VSW, indicated by a red and black barber pole. As speed approaches VSW, a gentle progressive nose-down pitch input is introduced to lower the nose and prevent further speed loss. The pitch input can be overridden by pilot input on the side stick. At VSW, an aural stall warning is triggered. The aircraft will stall if the warning is ignored. Alpha floor protection is inoperative in alternate law. In alternate law, high-speed stability replaces high-speed protection. The green dashes are replaced by amber dashes on the speed scale. Above VMO or MMO, a nose-up input is introduced to raise the nose and prevent further speed increase. This pitch tendency can be overridden by the pilots. As in normal law, if VMO-MMO is exceeded, the overspeed warning is triggered. Note that according to the failures, an alternate law without reduced protections can exist. In this case, only the maneuver protection is provided. The high-speed and low-speed stabilities are also lost. Stall and overspeed warnings are still operative. Direct law is the lowest level of computer flight control. Pilot inputs are now sent to the control surfaces unmodified. Because of the large number of failures required to degrade to direct law, it is unlikely to occur during normal flight. In direct law, you will get an ECAM warning as shown, and additional messages on the PFD. We will study them later on. Direct law, as the name implies, gives a direct relationship between side stick movement and the deflections of all surfaces. In effect, the A330 behaves like a conventional aircraft, and control sensitivity will depend on airspeed. In direct law, there are no protections available, although stall and overspeed warnings will sound at the appropriate speeds. Auto trim is not available. The crew must trim the aircraft manually. Use manual pitch trim is indicated on the PFD. Auto turn coordination and Dutch roll damping are also lost. All yaw control in direct law is through the rudder pedals. In the worst cases of failure, such as complete loss of flight control computer power supply, the aircraft will revert to mechanical backup mode. In this mode, the only method of pitch control is manual adjustment of the THS using the pitch trim wheel, provided either blue or yellow hydraulic system is available. Manual pitch trim only is indicated on the PFD. Lateral control is achieved in this mode using the rudder pedals and their mechanical linkage to the rudder, provided at least one hydraulic system is available. In most cases, e.g. by resetting the flight control computer, You will be able to recover from mechanical backup to either alternate or direct law, depending on the type of failure. We will now see a brief summary of the different laws and their associated protections. In normal law, all the protections are available. In alternate law, the pitch attitude protection and the bank angle protection are lost. Maneuver protection is kept. High and low speed stabilities are introduced. In alternate law, without reduced protections, the high speed and the low speed stabilities are also lost. Only the maneuver protection remains. In direct law, all the protections are lost and the aircraft handled as a conventional aircraft. In mechanical backup, no more flight envelope protection is left. The pitch control is performed via the pitch trim wheel and the lateral control through the rudder pedals, thanks to their mechanical linkages, provided the appropriate hydraulic systems are available. You have seen all the different laws and protections. Maybe you wonder how to recover if extreme conditions cause the aircraft to leave the protected envelope, e.g., you have been flipped over by a very severe turbulence. Here is the answer. If the limits of normal laws are exceeded, abnormal attitude laws become active. This is a safety feature to ensure that the flight control computers will never prevent the pilots recovering from an abnormal in-flight attitude. The flight control laws operate in alternate law without protections in pitch, except for load factor protection, and without auto trim. In roll, direct law is provided, with yaw in alternate. After recovery, controls remain in alternate law for pitch and yaw, and direct law in roll. After all these emotions, you will now see the normal operation modules. As part of the preliminary cockpit preparation, you will check that the flap position agrees with the lever position. The speed brake lever is in the retract position. Warning: if a flight control surface position does not agree with the lever position, check with the maintenance crew before applying hydraulic power. During the walk-around, you should ensure that all the flight control surfaces are undamaged and free of any contamination, e.g. snow or ice. The same check is performed on each side of the aircraft. During the cockpit preparation, the only check associated with the flight controls is to ensure that all flight control computers are in the lights out configuration. Notice that before engine start, the bank angle protection indicators are displayed in amber on the PFD. The side sticks are inoperative because there is no hydraulic power. Moving the side sticks will not affect the control surfaces. Before pushback, for your own comfort, it may be necessary to adjust the position of the seats and the armrests to easily handle the side stick. This is done by using the seat electrical controls and the armrest control knob. In the same way, it may be necessary to adjust the position of the rudder pedals. This is done using the rudder pedal adjuster. After engine start, the ground spoilers are armed by pulling the lever out. Lift the speed brake lever. A white band appearing around the base of the speed brake lever and the green memo "Ground spoiler armed" on the engine warning display indicate that the spoilers are now armed. Next, the rudder trim is zeroed by pushing the reset push button. Reset the rudder trim. The trim is now reset to 0. This is checked on the rudder trim panel. It can also be seen on the ECAM flight control page via a blue line displayed below the rudder scale. Note, the rudder trim rotary switch and the reset push button switch are not active during flight with the autopilot engaged. The takeoff memo normally appears during taxiing. For training purposes, we have displayed it now. The flaps should be set to their takeoff position, 1 plus F, 2 or 3. While the flaps are deploying, we will be looking at their indications on the engine warning display. To set the flaps, you need to lift up the lower part of the flap lever and then position it to the appropriate setting. Here, as an example, we will select flap 1. Select flap 1. As soon as a flap selection is made, blue markers appear on the engine warning display to show the selected flap and slat positions. A blue label shows which flap position has been selected. Here, 1. Also, as soon as a flap selection is made, the current flap and slat position green markers move. When the flaps and slats have reached their selected positions, all position indications turn from blue to green. The flaps takeoff memo on the engine warning display turns to green. Takeoff trim is set manually using the trim wheels. The pitch trim values are indicated on the scales beside the trim wheels. The takeoff trim has to be in the green range. Select either pitch trim wheel. The pitch trim position set may be seen on the ECAM flight control page during the flight control check when taxiing. The after start sequence for flight controls is complete. When the flaps are extended, the ailerons droop in order to increase lift. For configuration 1 plus F by about 5 degrees, for the other configuration by about 10 degrees. The aileron indexes are now pointing to a small white square which represents the new neutral position. A flight control check is completed at a convenient stage while taxiing, as on a conventional aircraft. On the PFD, the combined side stick deflection indicator is displayed as a white cross. The cross only indicates side stick deflections and does not indicate control surface position. The green bank angle protection indicators have also appeared, indicating normal yaw, as the aircraft is hydraulically powered. The side sticks become operable after first engine start, as soon as hydraulic power is available. On ground, the control surfaces directly respond to movements of the side sticks. This is the ground mode. As it is not possible to see the flight-controlled surfaces from the cockpit, the reaction to side stick or rudder pedal movement is monitored on the ECAM flight control page. The page is automatically called when either of the side sticks or either of the rudder pedals are moved. We will start the flight control check with the elevators by moving the side stick to its full back position. Move the side stick. The pilot non-flying checks on the ECAM page that the elevators have moved to their full up position. Move the side stick fully forward. The elevators have now moved to their full down deflection. Move the side stick back to neutral. With the side stick neutral, ensure that the elevators have returned to the neutral position. The flight controls are working in pitch. We will continue by checking the roll control. Move the side stick full left. You can see on the ECAM that the left aileron has moved fully up. The right aileron has moved fully down. The roll spoilers on the left wing have extended. Move the side stick full right. Now you can see that the left aileron is fully down. The right aileron is fully up. The right roll spoilers are extended. Move the side stick back to neutral. With the side stick neutral, ensure that the ailerons return to the neutral position and the spoilers are back in their stowed position. Now we will check the rudder. Before testing the rudder pedals, you need to press and hold the rudder pedal's disconnect button on the nose wheel steering handle to prevent any unwanted steering inputs. Press the pedal disconnect button. Now the rudder pedal movements will have no effect on the nose wheel steering. The right rudder pedal should now be pushed. Push the right rudder pedal. The rudder has moved to its full right deflection, so you should now push the left rudder pedal. Push the left rudder pedal. The rudder has moved to its full left deflection, so the pedals should be returned to their neutral position. Select either rudder pedal. The rudder pedal has returned to the neutral position, so the pedal disconnect button should be released. Release the pedal disconnect button. The pilot non-flying would now check his side stick for full movement and correct control response. Because the rudder pedals are mechanically linked, it is unnecessary to recheck them. The flight control check is now complete. After takeoff, the direct relationship between the side sticks and the control surfaces, ground mode, is gradually blended into the flight mode. In flight mode, the pilot, using his side stick, will set an aircraft attitude. With the side stick released, the flight control computers will maintain this attitude. When the autopilot is engaged, the side sticks are locked in their neutral position and the rudder pedals remain stationary. Neither will move, regardless of any autopilot input. One of the first actions for the crew after gear retraction is to disarm the ground spoilers. This is achieved by pushing the speed brake lever down. Disarm the ground spoilers. The white band at the base of the speed brake lever is no longer visible, and the ground spoiler armed message has disappeared from the engine warning display. For training purposes, let's suppose we have taken off in configuration 2. You are above acceleration altitude with the airspeed increasing. At or above F speed, minimum speed for flap retraction, the flaps can be retracted directly to flap 1. Retract the flaps to 1. Flap 1 is now set. Notice both slats and flaps are extended to the first position. This is 1 plus F configuration. The airspeed is increasing through S speed, minimum speed for slat retraction. Flap 0 would be normally selected at this stage. To demonstrate automatic flap retraction, we will delay this action. As the speed approaches VFE flap 1 plus F, the flaps will automatically retract fully. Notice the slats remain deployed in their first position. This is configuration 1. There is no automatic retraction of the slats. Set flap 0. Flap 0 is now set, which can be confirmed on the engine warning display. Notice that the slat flap indications have been simplified. The after takeoff actions are now complete. We will go directly to the descent phase. During descent, the speed brake may be used to increase the rate of descent, to correct the flight profile from above, or to slow down. During the initial approach phase, speed brakes may be used to increase the rate of deceleration. To use the speed brakes, you must first press down on the speed brake lever, which is spring-loaded into the retract position. Push down on the speed brake lever.
The speed brake lever can now be moved rearwards to any position, depending on the amount of drag required. Move the lever to half position.
For training purposes, we have called the ECAM wheel page for you to remind you of the indications. The indications are also shown on the ECAM flight control page. We are back to normal display. With some power on at least one engine, the speed brake message will flash amber. Retract the speed brake. The spoiler retraction can be confirmed on the engine warning display by the absence of the speed brake memo message. We have activated the approach for you. The airspeed decreases below the maximum speed for flap extension, or VFE, shown on the speed tape by amber dashes. Select flap 1. Notice that an airborne selection from flap 0 to flap 1 deploys the slats only. You cannot select flap 1 plus F from flap 0 in the air. The speed has now decelerated to below VFE for flap 2. Select flap 2. Flap 2 is set.
On the A330, when in Conf 2 or 3, the flap load relief system automatically retracts the flaps to the next further retracted position in case of VFE exceedance by more than 2.5 knots. In this case, the slats are maintained in their present position. Note, The overspeed activates an oral alarm and ECAM messages that are not presented in this module. When the speed decreases below VFE by more than 2.5 knots, the flaps return to the selected position.
At this point, before flap 3 is selected, we have lowered the landing gear for you. Arm the spoilers. The ground spoilers are armed, which can be confirmed on the engine warning display. Notice that as the landing gear is down, and as we are below 2,000 feet above ground level, the landing memo has appeared. Below VFE, flap 3 can now be selected. Select flap 3. Flap 3 is set. Although flap 3 may be used for landing, the normal configuration is flap full. Select flap full. Flap full is set, and the speed is constant at V approach, the final approach speed. You can check on the landing memo that the aircraft is now fully configured for landing. Passing 100 feet, the flight mode changes to flare mode. The flare is flown in direct yaw. At touchdown, with the main landing gear compressed, the ground spoilers deploy automatically and operate as lift dumpers, provided the thrust levers are at idle or reverse. Spoiler extension can be monitored by the pilot non-flying on the ECAM wheel page. Note: if only one main landing gear is compressed, the ground spoilers will extend partially, thereby decreasing the lift and compressing both main landing gear legs. Ground spoilers will then deploy fully. If a go-around is performed, the ground spoilers will automatically retract when the power is applied. As part of the after-landing phase, the ground spoilers should be disarmed. Disarm the ground spoilers. The flaps should now be retracted. Select flap 0. This concludes the normal operation of flight controls. Let's first see the redundancy aspects of the flight controls. In case of a computer failure, the second computer of the same type takes over. Each primary flight control surface is controlled by different hydraulic sources. 2 for the ailerons, elevators, and stabilizer. 3 for the rudder. Each control surface has an independent actuator for each hydraulic source. Each actuator is controlled by a different computer. One actuator for each surface is always in active mode. The other stays in damping mode and is monitored by its associated computer. To simplify the schematic, only some computers and a few of their associated links are shown. We will demonstrate these points in the following Sec 1 failure. Assume you are the pilot non-flying. You are in flight and everything is normal. Click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. Observe SEC indications on the ECAM flight control page. The 1 and the box around SEC 1 are amber. The 2 of SEC 2 remains green, indicating that SEC 2 has taken over automatically. The indication for the outer aileron actuator, controlled by SEC 1, is partially boxed in amber. This means that if this actuator was in active mode, it would have been automatically switched to damping mode. Here, as it is not the active one, it remains in damping mode. The active actuator, controlled here by Prim 3, is not boxed on the ECAM flight control page. Notice also the spoilers affected by the failure of SEC 1 are shown as faulty. The SEC 1 fault light is illuminated on the flight control panel. We can see that the first action is to reset the faulty computer. The pilot flying will ask you to perform the ECAM actions. Perform ECAM action. SEC 1. After review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. A green message advises us that we have a degradation in approach capability. You can see in the INOP Systems column that several systems are now inoperative. After review and confirmation from the pilot flying, clear status. ECAM actions completed. We will now review the other redundancy features and protections we did not have the opportunity to see when performing the previous procedure. In case of complete failure of Prim computers, SEC computers take over. SEC computers provide complete aircraft control in direct law. In the very low probability of SEC 1 failure, it will be replaced by SEC 2, or vice versa. Another case of failure is an elevator fault. In this case, the deflection of the remaining one is limited to avoid excessive asymmetrical loads on the tail or rear fuselage, and to reduce the asymmetry effects. The remaining surface is sufficient to resume normal flight. Provided the appropriate hydraulic systems are available, mechanical control of the THS is always available via the pitch trim wheels. For the rudder, mechanical control via the rudder pedals is always available, even in case of complete computer failure. This is called the mechanical backup. Summary. General rules. If a computer fails, the second computer of the same type takes over. Each primary flight control surface is supplied by at least 2 different hydraulic sources. An independent actuator is associated with each hydraulic source for each surface. Each actuator is controlled by a different computer. For a surface, one actuator is always in active mode, while the others are in damping mode. Ailerons, elevators, THS, rudder. If all three prim computers fail, SEC computers take over. If SEC 2 fails, it will be replaced by SEC 1, or vice versa. Mechanical backup is always available using the rudder pedals and pitch trim wheels, provided the appropriate hydraulic systems are available. Let's see how the spoilers are controlled. The spoiler control is shared by the prim and the SEC computers. We will now see a spoiler fault. Assume we are in descent, speed brakes extended, and no previous fault has occurred. Retract the speed brakes to activate the failure. On the engine warning display, read the title of the failure. Observe left spoiler 3 indication in amber on the ECAM flight control page. This indication means that left spoiler 3 has failed in the extended position. The SEC, which controls this spoiler and has detected the fault, will automatically retract it and inhibit the symmetrical one on the other wing, right spoiler 3, also shown in amber. You can now observe on the ECAM flight control page that spoilers 3 on both wings are retracted and shown in amber. Note that when a spoiler has failed on one wing, the symmetrical one is automatically inhibited except for spoilers 4 and 6. As a general rule, spoilers are automatically retracted when faulty or not electrically controlled. As no action is required by the procedure, after review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. You can see in the inoperative systems column that partial spoilers are now inoperative. After review and confirmation from the pilot flying, clear status. ECAM actions completed. We will now review the other spoiler aspects we did not have the opportunity to see when performing the previous procedure. Under certain circumstances, speed brake extension can be inhibited. In these cases, the spoilers are automatically retracted and stay in this position until the inhibition conditions no longer exist and the lever is reset. A master caution and an ECAM procedure are also triggered. Each spoiler is fitted with a single actuator, supplied by one of the hydraulic sources. In case of a loss of hydraulic supply, an affected spoiler remains at its current deflection unless pushed down by aerodynamic forces. Summary. Spoiler control is shared by the prim and SEC computers. When a spoiler has failed on one wing, the symmetrical one is automatically inhibited, except spoilers 4 and 6. As a general rule, spoilers are automatically retracted when faulty, inhibited, or not electrically controlled. Each spoiler is fitted with a single actuator supplied by one hydraulic source. In case of loss of hydraulic supply, an affected spoiler remains at its current deflection unless pushed down by aerodynamic forces. We have discussed spoiler faults. We will now see a double FC-DC failure. Assume that the aircraft has been dispatched with FC-DC2 faulty as authorized by the minimum equipment list. Notice that the status reminder is displayed on the engine warning display, called the status page. You can see that FC-DC2 is shown as inoperative. Select the flight control page. Observe, with a single FC-DC available, here FC-DC1, the ECAM flight control page indications are normal. Deselect the ECAM flight control page. Assume you are the pilot non-flying. You are in flight and, except for the FC-DC2, everything is normal. Click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. Observe on the ECAM flight control page that the data normally supplied by FC-DC1 or 2 is no longer available for display and is replaced by amber indications or crosses. As the procedure recommends not to use the speed brakes above flight level 200, you will have to check the flight control computer status by monitoring the left and right flight control panels on the overhead panel. Here, as no fault lights are illuminated, the other computers are all working. As no further action is required by the procedure, after review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. A green message advises us that the flight control indications are lost. You can see in the inoperative systems column that FC-DC 1 and 2 are now inoperative. After review and confirmation from the pilot flying, clear status. ECAM action completed. You have seen a double FC-DC failure. We will now see a turbulence damping fault. Assume you are the pilot non-flying. You are in flight and everything is normal. Click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. Notice that there are neither oral nor visual warnings, and also that the system page is not called. The turbulence damper function is inoperative. As no action is required in the procedure, after review and confirmation from the pilot flying, clear flight control. You can see in the inoperative systems column that the turbulence damper is now inoperative. After review and confirmation from the pilot flying, clear status. ECAM action completed. You have completed the second flight control abnormal module. Let's continue with the third episode. We will start with an SFCC 1 flap channel fault. Let's assume you are the pilot non-flying. You are in flight and everything is normal. Click on the forward arrow to activate the failure. Note that there are neither audio nor visual warnings in this case. The title of the failure is displayed on the engine warning display. SFCC1 flap channel is faulty. As the flaps information is displayed on the engine warning display, no system page is called. As no action is required, after review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. A cyan message advises us that we will have to switch GPWS flap mode off for the approach. Notice the green information, flaps slow. When an SFCC flap channel is inoperative, the flaps are still available, but they will move at half speed. If the two channels of one SFCC fail, both slats and flaps will operate at half speed. You can see that no inoperative system is displayed in the inoperative system column. After review and confirmation from the pilot flying, clear status. ECAM action completed. You have studied an SFCC channel failure. Let's see now another failure. You are now in the approach phase, and the slats and flaps need to be extended. Flap 1 has already been set for you. Set flap 2. On the engine warning display, read the title of the failure. Notice on the engine warning display that F locked and the flap triangle have turned amber, indicating that we have a flap fault. The amber F locked indicates that the flaps are locked. The white S and the green triangle indicate that the slats have reached the selected position. The flaps have been locked in position by the wingtip brakes, WTB, which are hydraulic devices. They lock the affected surface movement on both wings in case of asymmetry, overspeed, symmetrical runaway, or uncommanded movement. Note that they cannot be released in flight. If the flap's wingtip brakes are activated, slats operation is still possible, and vice versa. Notice you are restricted to flaps 2, limiting speed. After review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. The required landing configuration is flap 2. V approach and the landing distance will be increased to compensate for the locked flaps. Use the Quick Reference Handbook to determine the new V approach and landing distance. You can see in the Inoperative Systems column that the flaps are inoperative. After review and confirmation from the pilot flying, clear status. ECAM action completed. You have seen a flap locked fault. Let's assume we have no failure. You are the pilot non-flying and we are in approach. Flap 1 has been set and you are ready to set flap 2. Set flap 2. On the engine warning display, read the title of the failure. Notice on the engine warning display that S and the slat triangle have turned amber, confirming that we have a slat fault. We are restricted to VFE flap 2. The action is limited to the recycling of the flap lever. The pilot flying will ask you to perform the ECAM actions. Perform ECAM action. The flap lever is back to 1. Set it again to 2. Perform ECAM action. The slat recycling has not been successful. Notice that, in this case, the procedure steps stay on the engine warning display. After review and confirmation from the pilot flying, clear flight control. You can see that we are now in alternate law. The loss of the protections is confirmed on the primary flight display by the amber crosses at the roll limits and also at the pitch limits when visible. After review and confirmation from the pilot flying, clear flight control. The status page is displayed for review. A white approach procedure title shows us the procedure to apply for the approach. In this case, GPWS and flap settings. The approach and the landing distance will be increased to compensate for the faulty slats. Use the Quick Reference Handbook to determine the resulting landing distance. Observe the confirmation that we are in alternate law. You can see in the Inoperative Systems column that the flight control protections and the slats are inoperative. After review and confirmation from the pilot flying, clear status. ECAM action completed. We will now review some other slats and flaps protection features and indications. An amber caution message, flap MCDU disagree, is triggered in case of discrepancy between the real takeoff flap's position and the value entered in the MCDU performance takeoff page. The last protection feature is the slat's alpha speed lock function. This function inhibits slats retraction at high angle of attack and/or low speed. It is indicated by an A-lock pulsing green on the engine warning display.